On October 29th, something went behind our sun. For 2 weeks, every telescope on Earth went blind. When observation resumed, the largest sunspot in a decade had appeared, pointed directly at our planet. The interstellar object 3I/Atlas is now approaching its closest pass to Earth. December 19th, 269 million kilometers, and that sunspot, 90% the size of the one that caused the Carrington event in 1859, may rotate back to face us at the same moment. Coincidence is one explanation. But there are 8 others that science cannot dismiss. Tonight, we explore what happened during the hidden window, why a Harvard astrophysicist is asking questions no one wants to answer, and what the convergence of these 2 events might mean for everything we have built. The data is real, the timing is suspicious, and the next 2 weeks could be the most consequential in modern history. Before we begin, like and subscribe if this calm, science-driven format resonates with you. Use the hype button if it is available. In the comments, note your location, your current time, and the key question this topic triggers for you. I will address the strongest questions in comments or in a later video. On October 29th, 2025, at 7:47 in the morning Eastern Time, something slipped behind our sun. The interstellar object designated 3I/Atlas reached the closest point in its trajectory to our star, a distance of approximately 203 million kilometers, and at that exact moment, every telescope on Earth went blind to it. This was not a malfunction. This was geometry. Solar conjunction occurs when an object passes to the far side of the sun relative to our planet, placing our star directly between us and whatever we are trying to observe. The glare becomes absolute. The corona bleeds light in every direction, and for roughly 2 weeks, 3I/Atlas existed in a window of total invisibility. Think about that for a moment. The third interstellar object ever detected by human instruments, an ancient traveller that entered our solar system from the void between stars, chose this precise trajectory through billions of possible paths, and its closest approach to the sun happened during the one period when we could not watch it. Now, 5 weeks later, something else demands our attention. A sunspot complex has rotated into view on the Earth, facing disk of the sun. It carries the designations AR4294, AR4296, and AR4298. Together, they form one of the largest active regions observed in over a decade. The magnetic classification is beta, gamma, delta, the highest complexity rating our systems assign. This sunspot is capable of producing X-class solar flares. It is 90% the size of the sunspot that caused the Carrington event in 1859, the most devastating geomagnetic storm in recorded history. 2 events, one hidden, one revealed, both converging on Earth in December 2025. The question that will carry us through tonight is not whether these events are connected. Science does not yet have the instruments or the framework to answer that definitively. The question is simpler and more unsettling. What are the odds? Let us begin with what we know about the hidden window. 3I/Atlas was discovered on July 1st, 2025, by the Asteroid Terrestrial Impact Last Alert System telescope in Chile. Within days, astronomers recognized something extraordinary. The object was moving too fast to be gravitationally bound to our sun. Its trajectory was hyperbolic, meaning it would pass through our solar system once and never return. This made it only the 3rd confirmed interstellar visitor in human history, following Oumuamua in 2017 and Borisov in 2019. But 3I/Atlas was different from its predecessors in ways that immediately caught attention. Its speed at discovery was approximately 137,000 miles per hour, faster than either previous interstellar object. By the time it reached perihelion, that speed had increased to roughly 153,000 miles per hour. The object was ancient, with estimates placing its age between 7 and 11 billion years, older than our own solar system, and its path through our cosmic neighbourhood was suspiciously convenient. The trajectory of 3I/Atlas brought it within tens of millions of kilometres of Mars. It will pass close to Venus, it will approach Jupiter, and on December 19th, it will reach its closest point to Earth at a distance of 269 million kilometres. These planetary alignments are not impossible for a natural object, but they are statistically unusual. Harvard astrophysicist Avi Loeb calculated the probability of such a trajectory occurring by chance at approximately 0.005%, 1 in 20,000. And yet the most striking feature of the trajectory is not where 3I/Atlas went. It is when it went there. Perihelion, the closest approach to the Sun, represents a critical moment for any object in our solar system. At this point, gravitational forces are strongest, velocity is highest, and for any spacecraft this is the optimal moment for what physicists call an Obath maneuver. The Obath effect is a principle of orbital mechanics that has been understood for nearly a century. In simple terms, a propulsive burn performed at high velocity is more efficient than the same burn performed at low velocity. The deeper you fall into a gravitational well, the faster you move, and the more kinetic energy you can extract from your fuel. Every interplanetary mission we have ever launched has used this principle. It is fundamental to how we navigate the solar system. For 3I/Atlas at perihelion, the Sun was delivering approximately 33 gigawatts of solar radiation to its surface. That is 1/3 of the total nuclear power generation capacity of the United States. If the object had any capacity to harvest that energy, any mechanism to store it, any system to use it, perihelion was the moment of maximum power, and perihelion was hidden. Now consider the counter-argument. The solar conjunction of 3I/Atlas was not a choice. It was a consequence of orbital mechanics and the position of Earth in its own orbit around the Sun. If Earth had been on the opposite side of its orbit, we would have had a front row seat to the entire perihelion passage. The timing was coincidental, not designed. This is true, and it is also incomplete, because the trajectory of 3I/Atlas was set long before it entered our solar system. The path it follows was determined by its velocity and direction when it crossed the heliopause, the boundary where the Sun's influence ends and interstellar space begins. That crossing happened approximately 8,000 years ago. If the trajectory was calculated, if it was chosen, the calculation was made before human civilization had invented writing. We cannot know the intentions of something that old. We can only observe the outcome. The outcome is that 3I/Atlas performed its closest solar approach during a 2-week window of complete invisibility from Earth. Any course corrections, any deployments, any interactions with the solar environment, all of it happened where we could not see. And then something appeared. The sunspot complex AR429-4-4298 did not emerge from nowhere. Sunspots form through complex interactions in the solar magnetic field, processes that unfold over days and weeks in the convective zone beneath the Sun's surface. But the timing of its rotation onto the Earth, facing disk, is striking. As 3I/Atlas emerged from behind the Sun in early November, the sunspot complex rotated into view. By late November, it had grown to its current size, one of the largest active regions in solar cycle 25. Correlation is not causation. This is the first principle of scientific reasoning, and we must hold it firmly. The Sun produces large sunspots regularly during solar maximum. Solar cycle 25 has already exceeded predictions, with activity levels not seen in over 20 years. The appearance of a major sunspot complex in late 2025 is entirely consistent with normal solar behavior. But normal solar behavior does not usually coincide with the arrival of an interstellar object. Let me be precise about what we are not claiming. We are not claiming that 3I/Atlas caused the sunspot. We are not claiming that an alien intelligence used the object to trigger solar activity. We are not claiming that the December convergence represents any form of coordinated threat. These would be extraordinary claims requiring extraordinary evidence, and we do not have that evidence. What we are claiming is simpler. The timing is unusual, the geometry is suspicious, and the questions raised by this convergence deserve serious consideration, not dismissal. The mainstream scientific consensus holds that 3I/Atlas is a comet. It displays a coma, the fuzzy envelope of gas and dust that surrounds an active cometary nucleus. Spectroscopic analysis has detected carbon dioxide, cyanide, and other compounds consistent with cometary composition. NASA's official position, stated clearly in press releases and public communications, is that the object looks like a comet and does comet things. This consensus may well be correct, but it does not explain all the observations. 3I/Atlas survived its perihelion passage intact. This is notable because the object passed through a coronal mass ejection in late September, exposing it to temperatures exceeding 5,500 degrees Celsius. Many comets fragment under far less extreme conditions. The nucleus remained whole. 3I/Atlas is glowing bluer than the Sun. At perihelion, observations from space-based coronagraphs detected a colour shift that should not occur if the object is simply reflecting sunlight off dust particles. Dust reddens scattered light. Something about 3I/Atlas is producing excess blue emission, possibly from gas molecules, possibly from something else. 3I/Atlas contains an unusual ratio of nickel to iron. The gas plume surrounding the object shows nickel concentrations far higher than typical comets, in ratios more commonly associated with industrial alloys than natural ices. Each of these anomalies has a potential natural explanation. Taken together, they form a pattern that Loeb has rated as a 4 on his proposed scale of 0 to 10, where 0 represents a definitely natural object and 10 represents definitely artificial. A 4 is not high. It is not a claim of alien technology. It is a statement that the uncertainty is real, that the data does not yet allow us to close the question. And so, we watch, we wait, we gather data. The sunspot complex continues to rotate across the solar disk. In approximately 2 weeks, it will move to the far side of the Sun, temporarily removing the threat of Earth-directed flares. But sunspots can survive multiple rotations. AR 4294 may return around Christmas, pointing at us once again just as 3I/Atlas reaches its closest approach. December 19th, 269 million kilometres. The nearest an interstellar object has ever come to our planet while we had the technology to observe it. The hidden window is closed. But the questions it raised are just beginning to open. What happened behind the Sun on October 29th? What is the relationship between the ancient traveller and the wound that appeared on our star? And as both events converge on Earth in the final weeks of this year, what should we be watching for? The Sun does not answer. The comet does not explain. And the silence between them grows heavier with each passing day. There is a concept in astrophysics called the observation window. It refers to the narrow slice of time during which a transient event can be detected and studied, before it fades or moves beyond our instruments. For 3I/Atlas, the observation window was interrupted at the worst possible moment. We watched it approach for months, tracking its brightening, analysing its spectral signatures, debating its nature in scientific journals and social media threads. Then the geometry of our solar system pulled a curtain across the stage. What happened behind that curtain remains unknown. Space-based observatories attempted to peer through the glare. The Parker Solar Probe, orbiting closer to the Sun than any spacecraft in history, gathered data from its unique vantage point. The SOHO satellite, stationed at the first Lagrange point between Earth and Sun, captured images through its coronagraphs. The European Space Agency's JUICE mission, currently en route to Jupiter, passed within 64 million kilometres of 3I/Atlas on November 4th and turned its instruments toward the visitor. The data from these missions is still being processed. The analysis will take months, and in the meantime, the object continues its journey outward, growing fainter with each passing week. But the sunspot remains. AR 4294 sits on the solar disk like an open question, its magnetic field lines twisted into configurations that store enormous energy. At any moment, those field lines could reconnect, releasing their stored power in a flash of radiation and a wave of charged particles. The probability of an X-class flare from this region remains elevated. The probability of something larger, something approaching Carrington class intensity, is low but not zero. We live in a civilization built on electromagnetic infrastructure. Our power grids, our communications networks, our financial systems, our transportation, all of it depends on the stable flow of electrons through copper and silicon. A sufficiently powerful solar storm would induce currents in those systems that they were never designed to handle. Transformers would overload, satellites would fail, the cascading effects would ripple through every aspect of modern life. This is not speculation. This is the assessment of engineers and physicists who study space weather. The question has never been whether such an event will occur, only when. And now we find ourselves in December 2025, watching a sunspot of historic proportions while an interstellar object of uncertain nature approaches its closest pass to Earth. The hidden window has given way to a window of convergence. What we see through that window will depend on what we choose to look for. The wound on the Sun. The Sun has always marked itself. For billions of years before any eye existed to observe it, dark patches have appeared and faded on the solar surface, temporary blemishes on a star that burns at 5,500 degrees Celsius. We call them sunspots, though the name understates their nature. These are not spots. They are wounds in the magnetic fabric of our star, places where the internal pressure of twisted field lines breaks through the photosphere and creates regions cooler than their surroundings. Cooler is relative. A sunspot is still hot enough to vaporize any material known to human science. It appears dark only by contrast with the blazing surface around it. And the sunspot complex now facing Earth is not merely dark, it is dangerous. AR 4294 emerged in late November as the Sun continued its rotation, a cycle that takes approximately 27 days to complete from our perspective on Earth. By the time the region rotated fully into view, astronomers immediately recognized its significance. The area covered by the sunspot group approached 2,000 millionths of the visible solar hemisphere. To put that in terms we can grasp, the sunspot complex is large enough to swallow Earth 20 times over. But size alone does not determine danger. The critical factor is magnetic complexity. The Sun generates its magnetic field through a process called the solar dynamo, driven by the differential rotation of plasma in the convective zone beneath the surface. Near the equator, the Sun rotates faster than at the poles. This differential motion stretches and twists magnetic field lines, winding them tighter and tighter until they become unstable. When the twisted lines break through the surface, they create sunspots. Simple sunspots have a bipolar configuration, with magnetic field lines arcing from one polarity to another like the field of a bar magnet. These are classified as beta regions, and while they can produce flares, the energy release is typically modest. More complex regions develop additional magnetic polarities, creating tangled configurations where field lines from different sources interact. These are classified as beta, gamma regions. The most dangerous classification is beta, gamma, delta, indicating that opposite polarities exist within a single sunspot umbra, creating conditions of extreme magnetic stress. AR 4294 carries the beta, gamma, delta classification. The energy stored in these twisted magnetic configurations is almost incomprehensible. When field lines of opposite polarity are forced close together, they can suddenly reconnect, releasing their stored energy in a process called magnetic reconnection. The released energy accelerates particles to near light speed, heats plasma to tens of millions of degrees, and produces electromagnetic radiation across the entire spectrum, from radio waves to gamma rays. This is a solar flare. Flares are classified on a logarithmic scale. C. Class flares are common and cause minor effects. M. Class flares are moderate and can disrupt radio communications. X. Class flares are the most powerful, capable of causing radiation storms and widespread technological disruption. Within the X-class category, the numbers continue to climb. An X1 flare is significant. An X10 flare is severe. The Carrington event of 1859 is estimated to have been produced by a flare somewhere between X40 and X50. In the first week of December 2025, the sunspot complex AR 4294 through 4298 produced multiple C class flares and several M class events. On December 1st, the adjacent region AR 4299, which had previously rotated around the far side of the Sun, announced its return with an X 1.9 flare. This was the same region that produced major activity in mid-November, including an X 5.16 flare that was the strongest of the year. The Sun is not calm. The Sun has not been calm for months, and the largest sunspot complex of the current solar cycle is now pointed directly at our planet. Let me describe what happens during a major flare in terms that illuminate the physics. Imagine a rubber band stretched to its limit. The tension in the band represents stored energy. If you continue to stretch it, eventually it will snap, and all that stored energy will be released in an instant. Now imagine billions of rubber bands, each one twisted and tangled with its neighbours, all stretched to their breaking points simultaneously. When one snaps, it can trigger others. The cascade can release more energy in minutes than humanity has used in its entire history. The The solar flare itself travels at the speed of light. 8 minutes after the reconnection event on the Sun, the electromagnetic radiation reaches Earth. This includes not just visible light, but X-rays and ultraviolet radiation that ionize the upper atmosphere. Radio communications on the daylit side of the planet can be disrupted immediately. Airline pilots flying polar routes may lose contact with ground control. GPS signals can become unreliable, but the flare is only the beginning. Major flares are often accompanied by coronal mass ejections, or CMEs. These are vast clouds of magnetized plasma, billions of tons of solar material hurled into space at speeds that can exceed 2,000 kilometers per second. Unlike the electromagnetic radiation of the flare, CMEs are physical objects. They take time to cross the distance between the Sun and Earth, typically between 15 hours and several days depending on their velocity. When a CME strikes Earth's magnetosphere, the results can be spectacular and devastating. The magnetosphere is our planet's invisible shield, generated by the churning iron core thousands of kilometers beneath our feet. It deflects most of the charged particles streaming constantly from the Sun, but a powerful CME can compress and distort the magnetosphere, allowing particles to funnel down toward the poles and creating the phenomenon we know as the aurora. During normal conditions, the aurora borealis and aurora australis are visible only at high latitudes, typically above 60 degrees north or south. During major geomagnetic storms, the aurora can be seen much farther from the poles. During the Carrington event, people in Cuba and Hawaii saw red and green lights dancing across the sky. In Colombia, near the equator, the night became bright enough to read by. The beauty of the aurora masks its danger. As charged particles interact with Earth's magnetic field, they induce electrical currents in any long conductor. Power lines become antennas, picking up current from the sky. Pipelines develop voltage gradients. The rails of train tracks carry unexpected charges. And transformers, the massive devices that step voltage up and down throughout the electrical grid, can be overloaded by currents they were never designed to handle. In March 1989, a geomagnetic storm caused the collapse of the Hydro-Quebec power grid. 6 million people lost electricity for 9 hours. The storm that caused this blackout was approximately 3 times weaker than the Carrington event. In July 2012, a Carrington-class solar storm erupted from the Sun and crossed Earth's orbital path. By pure chance, our planet had passed that point in its orbit 9 days earlier. The storm missed us by a margin so narrow that only luck separated modern civilization from a potential catastrophe. The sunspot we are watching now has the capacity to produce such a storm. This is not speculation. This is the assessment of space weather forecasters at NOAA, at ESA, at observatories around the world. The beta, gamma, delta magnetic configuration of AR 4294 indicates stored energy sufficient for X-class flares. Whether that energy will be released while the sunspot faces Earth, whether any resulting CME will be directed toward our planet, whether the impact will be glancing or direct, these are questions that cannot be answered in advance. We can only watch, we can only prepare, and we can only wonder at the timing. The sunspot complex appeared as 3I/Atlas emerged from behind the Sun. This is a statement of chronology, not causation. The Sun produces large sunspots regularly during periods of high activity. Solar cycle 25 has been more active than predicted, with monthly sunspot numbers exceeding forecasts by significant margins. The appearance of a major sunspot complex in late 2025 is consistent with the behavior of our star during solar maximum. And yet, the Sun is a dynamic system of almost inconceivable complexity. We understand the broad principles of the solar dynamo, but the details remain elusive. We cannot predict exactly when sunspots will appear or how large they will grow. We cannot forecast with certainty which magnetic configurations will produce major flares. We know the physics, but the system is too complex for precise prediction. Could an external influence affect solar activity? The question sounds absurd at first. The Sun contains 99.8% of all the mass in our solar system. Its internal processes operate on scales of energy and matter that dwarf anything in human experience. The idea that a comet, even an interstellar one, could influence the Sun seemed like cosmic hubris. But consider the magnetic environment. 3I/Atlas passed through regions of intense solar magnetic field during its perihelion approach. the object itself may carry magnetic properties, either remnant magnetism from its formation, or induced fields from its interaction with the solar wind. At the speeds involved, any interaction between the object's magnetic signature and the Sun's complex field structure would have been brief but potentially significant. We do not have data from the perihelion passage. The hidden window prevented direct observation. We do not know what happened when 3I/Atlas was closest to the Sun, travelling at maximum velocity through the most intense magnetic environment it would ever encounter. What we know is what came after. A sunspot complex of historic proportions, emerging on the Earth, facing disk precisely as the interstellar visitor re-emerged from solar conjunction. A magnetic configuration capable of producing flares that could threaten technological civilization. A timing so precise that it demands attention even if it defies explanation. The Sun has wounded itself before, it will wound itself again. The question hanging over December 2025 is whether this particular wound is coincidence or consequence. The wounded star continues to rotate. The sunspot complex drifts slowly toward the western limb, each day reducing the angle at which any flare would strike Earth. In approximately 2 weeks, AR 4294 will rotate out of view, passing to the far side of the Sun where its tantrums cannot directly affect our planet. But sunspots can survive multiple rotations. The magnetic structures that produce them persist beneath the surface, even when the visible manifestation disappears. AR 4294 may return around Christmas, rotating back onto the Earth, facing disk just as 3I/Atlas reaches its closest approach. December 19th, 269 million kilometers. An interstellar object at its nearest point to our world, and potentially a historic sunspot pointed once again at the planet that ancient traveller has been approaching for 8,000 years. The wound on the Sun may be about to tear open again. The physics of sunspot evolution is complex and not fully understood. Magnetic flux emerges from the solar interior, creating the dark regions we observe on the photosphere. Over time, the flux can disperse, spreading across the solar surface and losing the concentration that defines a sunspot. Or it can persist, maintaining its coherence through multiple rotations. The factors that determine which path a sunspot will take are not entirely predictable. Larger, more complex regions tend to persist longer. Regions embedded in active zones with ongoing flux emergence may be reinforced by new magnetic material, but exceptions exist in both directions. AR 4294 is a member of a larger active complex that has been producing sunspots for weeks. The underlying magnetic structure suggests ongoing activity in the convection zone beneath. This is a favourable indicator for persistence. The sunspot may survive its rotation around the far side and return to face Earth. If it does return, the timing could be extraordinary. December 19th marks the closest approach of 3I/Atlas to Earth. December 25th, give or take a day or two, marks the expected return of AR 4294 to the Earth, facing disk if it survives the rotation. The week between these dates represents the peak of the convergence. A flare during this window would produce effects on Earth within 8 minutes, the light travel time from Sun to planet. A coronal mass ejection would follow in 15 to 36 hours, depending on its speed. The impact would coincide with the presence of an interstellar visitor at its nearest point. The coincidence does not prove connection. The Sun has no knowledge of comets passing through its system. The object has no power over solar magnetic fields, so far as we understand physics. The timing is what it is, remarkable but presumably meaningless. And yet the convergence invites attention. It focuses the mind on possibilities that might otherwise remain abstract. The threat of space weather becomes vivid when a historic sunspot faces our planet. The mystery of interstellar visitors becomes urgent when one approaches its closest pass. We cannot control the Sun. We cannot redirect the comet. We can only observe and prepare and hope that the wound heals before it bleeds again. The Carrington equation. On the morning of September the 1st, 1859, the English astronomer Richard Carrington was doing what he did most days. He was watching the Sun. Carrington had built a reputation for meticulous solar observation. Working from his private observatory in Redhill, south of London, he tracked sunspots with an attention to detail that few could match. He had already made significant contributions to our understanding of solar rotation, demonstrating that the Sun does not spin as a solid body, but rotates faster at the equator than at the poles. On this particular Thursday morning, he was sketching a large group of sunspots when something unprecedented occurred. A brilliant flash of white light erupted from the sunspot group. It lasted only 5 minutes, but its intensity was extraordinary, bright enough to be visible against the blazing disk of the sun itself. Carrington immediately understood he was witnessing something new. He rushed to find a witness, but by the time he returned the flash had faded. He was not the only observer. Richard Hodgson, another English astronomer working independently, had seen the same event. Their simultaneous observations would later prove crucial in establishing that the flash was real and not an artifact of equipment or perception. Carrington suspected a connection between the solar flare and terrestrial effects, but he was cautious. When the most intense geomagnetic storm in recorded history struck Earth the following day, he wrote that one swallow does not make a summer. He understood that correlation required careful verification before it could be claimed as causation. What happened on September 2nd, 1859, defied easy explanation for the science of its time. Telegraph systems across Europe and North America failed catastrophically. Operators reported receiving electrical shocks from their equipment. Telegraph paper caught fire, pylons threw sparks, and in one of the most remarkable details of the event, some operators discovered they could continue sending and receiving messages even after disconnecting their power supplies. The aurora itself was providing enough current to operate the equipment. The aurora that night was visible around the world. In the Rocky Mountains, gold miners woke and began preparing breakfast, convinced that dawn had arrived early. In the northeastern United States, people reported being able to read newspapers by the light of the sky. In the Caribbean, in Hawaii, in places that had never seen the northern lights, the sky glowed red and green with colours that seemed impossible. The geomagnetic storm lasted for days. When it finally subsided, the world returned to normal. The telegraph lines were repaired, the operators recovered from their shocks, and the event passed into scientific literature as a curiosity, a demonstration of solar power that few expected to see repeated in their lifetimes. 166 years later, we live in a civilization that the telegraph operators of 1859 could not have imagined. Every aspect of modern life depends on electromagnetic systems. The power that flows through our homes comes from generators connected by thousands of kilometers of high voltage transmission lines. The communications that link us span satellites in orbit, fiber optic cables beneath the oceans, and wireless signals bouncing from tower to tower across continents. Our financial systems process transactions through data centers that consume more electricity than small nations. Our transportation depends on GPS signals beamed from satellites that would be among the first casualties of a major geomagnetic storm. The Carrington event did not destroy civilization in 1859 because civilization did not yet depend on technology that could be destroyed. We had telegraph lines and nothing else. The storm was an inconvenience, a wonder, a scientific puzzle. It was not an existential threat. Today, the equation has changed. Let me walk through what would happen if a Carrington-class geomagnetic storm struck Earth tomorrow. This is not speculation. This is the analysis of engineers, physicists, and policy experts who have studied the problem in detail. The first warning would come from satellites positioned at the first Lagrange point, approximately 1.5 million kilometers sunward from Earth. The Deep Space Climate Observatory and similar spacecraft monitor the solar wind continuously. When a fast-moving CME approaches, these instruments detect the change in particle density and magnetic field orientation. The warning time depends on the speed of the CME, ranging from as little as 15 minutes for the fastest events to perhaps an hour for slower ones. 15 minutes is not enough time to do much. The CME would strike Earth's magnetosphere like a wave hitting a seawall. The magnetosphere would compress on the sunward side and stretch on the night side. Magnetic field lines would reconnect, dumping energy into the upper atmosphere. Currents would begin to flow. These are not the currents we use. These are geomagnetically induced currents, created when the changing magnetic field interacts with long conductors on Earth's surface. Power transmission lines become enormous antennas, picking up current from the fluctuating field. The longer the conductor, the greater the induced voltage. Transcontinental power lines, which can stretch for thousands of kilometers, would experience the largest effects. Transformers are the critical vulnerability. Electrical power is transmitted at high voltage because high voltage reduces resistive losses over long distances. At the generating plant, transformers step voltage up. At substations near consumers, transformers step voltage down. These devices are massive, expensive, and difficult to manufacture. A large power transformer weighs hundreds of tons and costs millions of dollars. More importantly, they are built to order. There is no stockpile of spare transformers waiting to replace damaged units. Geomagnetically induced currents can destroy transformers in minutes. The DC component of the induced current saturates the transformer core, causing it to overheat. The windings can melt, the insulating oil can catch fire, and once the transformer fails, the power it handled has to go somewhere else, potentially overloading the next transformer in the chain. The 1989 Quebec blackout demonstrated this cascade on a limited scale. A geomagnetic storm approximately 3 times weaker than the Carrington event triggered a sequence of failures that brought down the entire Hydro-Quebec grid in 90 seconds. 5 million people lost power for 9 hours. Transformers were damaged in New Jersey. Fluctuations rippled through the interconnected North American grid. A Carrington-class event would be orders of magnitude worse. Studies commissioned by the US government and by Lloyd's of London have attempted to estimate the damage. The numbers are staggering. Direct damage to electrical infrastructure could exceed $600 billion in the United States alone. Total economic impact, including cascading effects on other sectors, could reach $2.6 trillion. Power outages in some regions could last not hours or days, but months, possibly years. Consider what happens when the power goes out and does not come back on. Hospitals have backup generators, but those generators require fuel. Without power, fuel pumps at gas stations do not work. Without fuel, trucks cannot deliver supplies. Without supplies, the generators run dry. Medical equipment fails. Refrigeration fails. Food spoils. Water treatment plants shut down. Sewage systems back up. Modern cities are not designed for extended power loss. The population density that makes urban life efficient becomes a liability when supply chains collapse. Food in a typical supermarket represents approximately 3 days of local consumption. Warehouses hold more, but without transportation to move goods from warehouse to store, the reserves are inaccessible. Communications would fail almost immediately. Cellular networks depend on towers that require power. Internet infrastructure depends on data centers that require cooling. Satellite communications depend on ground stations that require electricity. The systems we use to coordinate emergency response would be among the first casualties of the emergency. This is not a scenario from science fiction. This is the assessment of experts who study infrastructure resilience. The United States Federal Energy Regulatory Commission has acknowledged the risk. The United Kingdom Royal Academy of Engineering has issued reports. The insurance industry has quantified potential losses. Everyone who examines the problem reaches similar conclusions. We are vulnerable. We are not prepared. And the sun does not care about our preparations. The probability of a Carrington-class event in any given year is low. Estimates range from approximately 1% to 12% per decade, depending on the statistical models and historical data used. Over a human lifetime, the cumulative probability becomes significant. Over the lifetime of our current electrical infrastructure, the question shifts from whether such an event will occur to when. Some preparations are possible. Utilities can install devices that detect geomagnetically induced currents and trip circuits before transformers are damaged. Grid operators can reduce loads during storm warnings, decreasing the stress on vulnerable components. Governments can stockpile critical transformer components, though the cost and logistics are challenging. But these preparations require time, money, and political will. They require acknowledging a threat that seems abstract and distant until it arrives without warning. And now we sit in December 2025, watching a sunspot complex capable of producing the flares that drive such storms. The beta, gamma, delta magnetic configuration of AR4294 indicates stored energy sufficient for major events. Whether that energy will be released in our direction remains unknown. The Carrington event happened near the peak of solar cycle 10. We are near the peak of solar cycle 25. The historical parallel is not exact, but it is close enough to merit attention. Richard Carrington watched the sun because he was curious. He recorded what he saw because he believed in the value of systematic observation. He could not have known that his careful notes would become the benchmark against which future solar storms would be measured. We watch the sun now for different reasons. We watch because our civilization depends on it. We watch because the equation has changed, and the terms now include everything we have built. We watch because somewhere behind that blazing disk, an interstellar visitor recently made its closest approach, hidden from our eyes during the moment of maximum potential. The Carrington event was a warning written in aurora and sparks. We have had 166 years to heed it. The sunspot facing Earth today will tell us whether we have learned anything at all. Beyond the immediate threat, there are longer-term considerations that deserve attention. The Carrington event was not unique in Earth's history. Ice core samples from Antarctica and tree ring data from around the world have revealed evidence of even larger solar events in the distant past. The Miyake event of 774 AD produced a spike in carbon-14 that suggests a solar storm roughly 20 times more powerful than the Carrington event. Similar spikes have been identified at other points in the geological record. These ancient events occurred before human civilization had developed electromagnetic infrastructure. They left traces in the chemistry of polar ice and the growth rings of trees, but they caused no technological damage because there was no technology to damage. We are no longer so fortunate. The Sun is not becoming more active over historical timescales. The frequency of major events has remained roughly constant for billions of years. What has changed is our vulnerability. Each new satellite launched, each new power line strung, each new data center built, adds to the infrastructure that would be affected by a major geomagnetic storm. The trend is accelerating. The space economy is expanding. The electrification of transportation is advancing. The digitalization of finance and commerce continues. Every step toward a more connected, more electronic civilization increases our exposure to space weather. And yet investment in space weather monitoring and infrastructure, protection remains modest. The warnings are clear, the probabilities are known, the potential consequences have been extensively documented. Still, the preparations lag behind the need. Perhaps this is human nature. We are not good at responding to threats that are rare, unpredictable, and impersonal. The Sun will not give us advance notice of its intentions. The storm will arrive when it arrives, whether we are ready or not. December 2025 finds us watching and waiting. The sunspot rotates. The interstellar visitor approaches. The convergence unfolds according to physics we understand but cannot control. Whatever happens next, the Carrington equation remains unchanged. Vulnerability multiplied by impact multiplied by probability equals risk. The first two factors have been growing for a century. The third is a matter for the Sun to decide. 9 anomalies and 1 question. Science proceeds by measuring differences. When an observation matches our predictions, we note it and move on. When an observation deviates from expectation, we pay attention. The larger the deviation, the greater the attention. And when multiple deviations cluster around a single object, the attention becomes intense. 3i/Atlas has accumulated 9 documented anomalies since its discovery in July. Each one, considered in isolation, admits a natural explanation. Comets are diverse objects. Interstellar visitors come from environments we cannot directly study. The unexpected is not the same as the inexplicable. But 9 anomalies is a lot of anomalies. Let me walk through them systematically, because understanding what makes this object unusual is essential to understanding why the questions persist. The first anomaly is the trajectory alignment. When an object enters our solar system from interstellar space, it can arrive from any direction. The galaxy surrounds us in 3 dimensions. Interstellar objects should be distributed more or less randomly across the celestial sphere, with no preferred orientation. 3i/Atlas entered our solar system at an angle within 5 degrees of the ecliptic plane. The ecliptic is the flat disk containing the orbits of the planets, defined by Earth's orbital path around the Sun. For a random interstellar object to align so closely with this plane is statistically unusual. The probability is approximately 0.2%, or 1 in 500. 1 in 500 is not impossible. It is not even particularly rare by astronomical standards, but it is the first deviation from expectation. The second anomaly is the timing of planetary approaches. The trajectory of 3i/Atlas brought it within tens of millions of kilometers of Mars in October, will bring it close to Venus, and will take it past Jupiter in early 2026. These close approaches to multiple planets, combined with the ecliptic alignment, create a path that seems almost designed to survey the solar system. Avilobe calculated the combined probability of this trajectory occurring by chance at approximately 0.005%, or 1 in 20,000. This calculation has been criticised by other astronomers who argue that the method overestimates the unlikelihood, but even critics acknowledge that the trajectory is unusual. The third anomaly is the solar conjunction at perihelion. As we have discussed, 3I/Atlas reached its closest approach to the Sun while positioned on the far side of our star relative to Earth. This geometry prevented direct observation during the most dynamic phase of the object's journey. The hidden window lasted approximately 2 weeks, coinciding precisely with the moment of maximum gravitational influence and maximum solar heating. A natural object does not choose its trajectory. The conjunction was a consequence of orbital mechanics and the position of Earth at the time of perihelion. And yet, if one were designing a trajectory to minimize observation during a critical maneuver, this is exactly what it would look like. The fourth anomaly is the anti-tail. Comets typically display tails that point away from the Sun, pushed by solar radiation and the solar wind. The dust tail curves gently, following the comet's orbital path. The ion tail points directly away from the Sun, a straight line of glowing gas. 3I/Atlas has displayed what observers call an anti-tail, a structure pointing toward the Sun rather than away from it. Anti-tails can occur naturally, when Earth passes through the orbital plane of a comet, and we see the dust tail from a different angle. The geometry can create an optical illusion of forward-pointing material. But some observers have argued that the anti-tail of 3I/Atlas is not adequately explained by viewing geometry. Loeb has suggested it might represent material being ejected forward, perhaps as a protective buffer against debris in the asteroid belt. This interpretation remains controversial. The fifth anomaly is the mass. By analysing the outgassing rate and the gravitational influence on the object's trajectory, researchers have attempted to estimate the mass of 3I/Atlas. The results suggest a mass exceeding 33 billion tons, far larger than typical comets, and roughly 1 million times the estimated mass of Oumuamua. Mass matters because it affects how an object responds to external forces. A more massive object is less affected by the push of outgassing, by the pressure of solar radiation, by the buffeting of the solar wind. If 3I/Atlas is as massive as these estimates suggest, its trajectory would be more stable than a typical comet's, more predictable, more controlled. The sixth anomaly is the chemical composition. Spectroscopic analysis of the gas surrounding 3I/Atlas has revealed an unusual ratio of nickel to iron. In most comets, these metals are present in roughly solar proportions, reflecting the composition of the primordial material from which the solar system formed. In 3I/Atlas, nickel dominates. This nickel, rich composition is more commonly associated with industrial alloys than with natural ices. The finding has prompted speculation about artificial origins, though natural explanations remain possible. The object may have formed in an environment with different elemental abundances than our solar system. The seventh anomaly is the water content. Comets are often described as dirty snowballs, bodies composed primarily of water ice mixed with dust and rock. The water content of a typical comet can be substantial, driving the characteristic activity that creates the coma and tail. 3I/Atlas contains only approximately 4% water by mass. This is far lower than typical comets, suggesting either a different formation environment or a history that removed most of the water. An object that spent billions of years in the cold of interstellar space might be expected to retain its volatile ices, not lose them. The eighth anomaly is the polarization. Light reflected from cometary dust becomes polarized, with the electric field oscillating preferentially in certain directions. The degree and type of polarization provides information about the size and composition of dust particles. 3I/Atlas has shown extreme negative polarization, unprecedented among all known comets, including Borisov, the previous interstellar comet. The polarization signature suggests dust properties, unlike anything previously observed in cometary environments. The ninth anomaly emerged at perihelion, as 3I/Atlas approached its closest point to the Sun, space-based observatories detected a color shift. The object appeared bluer than the sun itself. This is the opposite of what physics predicts. Dust scatters sunlight in ways that typically redden the colour, not blue it. The surface of a cold object should appear redder than the sun, not bluer. The blue colour suggests either an unusual emission source or a power source hotter than the solar photosphere. Neither explanation fits comfortably within standard cometry models. 9 anomalies, 9 deviations from expectation, 9 data points that do not quite fit the template of a natural comet. Loeb has proposed a rating scale for interstellar objects ranging from 0 to 10. 0 represents an object that is definitely natural. 10 represents an object that is definitely artificial. Based on the accumulated evidence, he currently rates 3I/Atlas at 4. A 4 is not a claim of alien technology. It is a statement that the uncertainty is significant. The natural explanation remains more likely than the artificial one, but the margin is not overwhelming. Critics have responded forcefully. They point out that each anomaly has potential natural explanations. Trajectory alignment could be coincidence, chemical composition could reflect, formation conditions in another star system. The blue colour could result from unusual gas emissions. Extraordinary claims require extraordinary evidence, and the evidence for artificial origin is circumstantial at best. This criticism is valid. The scientific method demands skepticism of unusual claims, especially claims that would overturn our understanding of our place in the universe. The default assumption should be that 3I/Atlas is a natural object, until and unless the evidence forces a different conclusion. But the critics have not made the anomalies disappear. They have offered alternative explanations, not definitive refutations. The data remains ambiguous. And now we arrive at the question that hovers over all of this. What are the odds? 9 anomalies, each individually explainable, cluster around a single object. That object arrives during the peak of solar maximum, when our star is most active and most dangerous. Its closest approach to the Sun occurs during a 2-week window of invisibility from Earth. A massive sunspot complex appears as the object emerges from behind the Sun, and the object's closest approach to Earth coincides with the potential return of that sunspot to the Earth. Facing disk, each piece can be explained separately. The trajectory is unusual but possible. The composition is strange but not impossible. The timing is suspicious but could be coincidental. The sunspot is natural and expected during solar maximum. But what are the odds of all of it together? This is not a question science can easily answer. Statistics deals with well-defined probability spaces with events whose likelihood can be calculated from known distributions. The arrival of an interstellar object is not such an event. We have 3 data points in the entire history of human observation. We cannot calculate the probability of unusual trajectories because we do not know the underlying distribution. What we can do is notice patterns. We can observe that multiple unusual features cluster around a single moment in time. We can acknowledge that the timing is striking even if we cannot prove it is meaningful. The 9 anomalies of 3I/Atlas may be nothing more than cosmic coincidence, a natural object from an unusual environment following an unusual path through our solar system. This is the most likely explanation. This is where the evidence currently points. But the question persists. In the silence between the data points, in the gap between observation and explanation, the question will not go away. What if we are looking at this all wrong? The Obath maneuver. In 1929, a Romanian physicist named Herman Obath published a book that would change how we think about travelling through space. The book was called Ways to Spaceflight, and buried within its pages was a counterintuitive principle that would eventually guide every interplanetary mission humanity has ever launched. The principle is simple to state, but strange to grasp. A rocket engine is more efficient when the vehicle is moving fast than when it is moving slow. The same amount of fuel produces more change in velocity at high speed than at low speed. This seems wrong at first. Fuel is fuel. Thrust is thrust. How can the same engine behave differently depending on how fast it is already travelling? The answer lies in the relationship between kinetic energy and velocity. Kinetic energy increases with the square of velocity. If you double your speed, you quadruple your kinetic energy. This nonlinear relationship means that adding velocity to an already fast-moving object increases its energy more than adding the same velocity to a slow-moving object. A rocket engine produces thrust by expelling mass at high speed. The reaction pushes the spacecraft forward, but the energy delivered to the spacecraft depends on the reference frame. When the spacecraft is moving fast, the exhaust is left behind with less total energy relative to the destination. More of the chemical energy from the fuel ends up as kinetic energy of the spacecraft. This is the Obath effect. In practical terms, the Obath effect means that the best time to fire your engines is when you're moving fastest. And when do you move fastest? At the bottom of a gravitational well. The closer you fall toward a massive body, the faster you go. The faster you go, the more efficient your burn. Every gravity assist maneuver exploits this principle. When Voyager swung past Jupiter, it used the planet's gravity to accelerate toward the outer solar system. When Parker's solar probe dives close to the Sun, it uses the Sun's gravity to reshape its orbit. The gravitational field provides free energy, and the Obath effect maximizes the benefit. Now consider 3I/Atlas at perihelion. On October 29th, the interstellar visitor reached its closest approach to the Sun at a distance of approximately 203 million kilometers. At that moment, it was traveling faster than at any other point in its journey through our solar system. The velocity exceeded 150,000 miles per hour. The gravitational acceleration from the Sun was at maximum. The conditions for an Obath maneuver were optimal. If 3I/Atlas is a natural comet, this moment was simply the low point of its hyperbolic orbit. The object swung around the Sun, gained no net energy from the gravitational interaction, and continued on its outward trajectory. Physics happened, indifferent to any observer, but if 3I/Atlas is something else, perihelion was an opportunity. The energy available at perihelion was enormous. Solar radiation at that distance delivers approximately 770 watts per square meter to any surface facing the Sun. For an object with a diameter of several kilometers, the total power received would be measured in gigawatts. This is comparable to the output of major nuclear power plants delivered for free by our star. What could be done with that power? If the object carried any form of energy storage, it could have collected solar radiation during the perihelion passage. Photovoltaic cells, thermal collectors, or more exotic energy harvesting systems could have captured a portion of the incoming flux. The stored energy could then be used for propulsion, for powering onboard systems, for purposes we cannot anticipate. If the object carried any form of propulsion, perihelion was the optimal moment to use it. A small velocity change at perihelion translates into a larger change in the final trajectory than the same velocity change applied elsewhere. The Obath effect magnifies the impact of any propulsive burn. If the object carried any payload intended for deployment, perihelion offered advantages beyond mere efficiency. The intense solar heating would have provided thermal energy for any processes requiring heat. The gravitational forces would have been at maximum, potentially useful for separation dynamics, and the solar conjunction meant that any deployment would have been hidden from Earth-based observation. This last point deserves emphasis. For approximately 2 weeks around perihelion, 3I/Atlas was unobservable from Earth. Telescopes could not penetrate the solar glare. Our best instruments were blind. During this window, anything could have happened and we would not have seen it. What might we have missed? Loeb suggested the possibility of a mothership scenario. In this hypothesis, the main body of 3I/Atlas would continue on its original trajectory, visible and trackable. But smaller objects released during the perihelion passage could follow different paths. These hypothetical mini-probes could use the gravitational slingshot effect to redirect toward other destinations, toward Mars, toward Venus, toward Earth. The physics is not speculative. We use exactly these techniques in our own space missions. The mathematics of gravitational assists has been understood for decades. If an advanced civilization wished to seed our solar system with observational platforms, perihelion passage would be an excellent opportunity to do so. But would we have seen the separation? This is where the hidden window becomes significant. Tidal forces from the Sun at perihelion could have provided natural-looking cover for any deployment. Comets sometimes fragment under solar heating. Pieces break away from the main nucleus and follow slightly different trajectories. If 3I/Atlas released objects during perihelion, they might initially appear as natural fragments. Over time, however, any propulsive adjustment would cause the fragments to diverge from purely gravitational paths. The tidal forces of the Sun would separate objects on natural trajectories from objects on powered trajectories. By December, any significantly different paths should become detectable through careful observation. This is what astronomers are watching for. The international observation campaign that resumed in November is not simply tracking the main body of 3I/Atlas. It is searching for any associated objects, any fragments, any unexplained companions. The Hubble Space Telescope, the James Webb Space Telescope, ground-based observatories around the world, all are contributing to a systematic survey of the region around the interstellar visitor. So far, no confirmed detections of secondary objects have been announced. The main nucleus appears intact. The trajectory remains consistent with purely gravitational motion, with no evidence of propulsive maneuvers. But the observation campaign is ongoing. The data is still being collected, and the question of what happened during the hidden window remains open. Let me be clear about what we are not claiming. We are not asserting that 3I/Atlas performed an Obath maneuver. We are not claiming that it released probes toward Earth or any other destination. We are not announcing the discovery of artificial objects in our solar system. What we are doing is acknowledging a gap in our knowledge. The perihelion passage occurred during a period when observation was impossible. The physics of the situation would have favoured any propulsive action. The Obath effect would have maximised the efficiency of any velocity change. The solar conjunction would have hidden any deployment from terrestrial detection. If 3I/Atlas is a natural comet, this gap in observation is merely an inconvenience. The object swung around the Sun and continued on its way. We missed the most dramatic part of the show, but nothing unusual happened. If 3I/Atlas is something else, the gap is a window of opportunity. The hidden window was not just a limitation of our observation, it was a moment when an artificial object could have acted without being watched. We do not know which interpretation is correct. The evidence currently favours the natural explanation. A comet, even an unusual one, is more likely than an alien spacecraft. Occam's razor suggests we should prefer the simpler hypothesis until the evidence demands otherwise. But the hidden window prevents us from closing the question definitively. We cannot prove that nothing happened at perihelion. We can only observe what came after and look for anomalies that would suggest something did happen. The sunspot that appeared as 3I/Atlas emerged from behind the Sun may be one such anomaly, or it may be coincidence. We do not know. The trajectory of 3I/Atlas in the coming weeks will be another data source. If the object continues on a purely gravitational path, that supports the natural interpretation. If any deviation is detected, any unexplained acceleration or deceleration, that would require explanation. The presence or absence of secondary objects will be informative. If fragments appear that were not expected, from natural cometary processes that would be significant. If no unusual companions are detected, that supports the conclusion that the perihelion passage was uneventful. We are watching, we are measuring, we are waiting. The Obath maneuver is a proven technique. We use it in our own spacecraft. The physics is well understood. The only question is whether an interstellar visitor used it too. Perihelion has passed, the hidden window has closed, but the implications of those 2 weeks will echo through December and beyond as 3I/Atlas continues its journey toward its closest approach to Earth. What happened at perihelion? We may never know for certain, but the question itself is worth asking, because the answer, whatever it is, matters. The physics of stellar flybys has been studied extensively, though primarily in the context of our own spacecraft rather than incoming visitors. Every deep space mission uses gravity, assists to shape its trajectory. The Voyager probes used Jupiter's gravity to accelerate toward the outer planets. Cassini used Venus, Earth, and Jupiter before reaching Saturn. New Horizons used Jupiter to shorten its travel time to Pluto. The mathematics is well understood. A spacecraft approaching a massive body gains velocity as it falls into the gravitational well. If it passes behind the body relative to the body's motion through space, it steals some of the body's orbital momentum, accelerating in the process. If it passes in front, it gives momentum back and decelerates. For 3I/Atlas, the Sun provided the gravitational well. The object's trajectory carried it around the back of the Sun relative to the Sun's motion through the galaxy. This geometry would have provided a small boost to the object's velocity, though the effect is negligible for an object already travelling at interstellar speeds. But the Obath effect operates independently of simple gravity assists. The efficiency gained from burning propellant at high velocity applies regardless of the geometry. At perihelion, 3I/Atlas was moving at its maximum velocity. Any propulsive action at that moment would have been maximally efficient. Consider what could be accomplished with even modest propulsion at perihelion. A velocity change of 1 meter per second, hardly more than a walking pace, would alter the trajectory enough to be detectable over the following months. Astronomers are watching for exactly such deviations. The non-gravitational acceleration observed in Oumuamua was on this order of magnitude, approximately 1 millimeter per second squared at perihelion. For Oumuamua, the cause of this acceleration remains disputed. Outgassing of invisible volatiles is the leading natural explanation, but the mechanism has not been definitively established. If 3I/Atlas shows similar anomalous acceleration, the same debate will likely recur. A larger velocity change could redirect the trajectory entirely. At interstellar, speeds, even small angle changes translate into vast differences over time. An object passing through our solar system on one trajectory could, with sufficient propulsion at perihelion, depart on a completely different heading. We would eventually detect such a change. The orbital mechanics are precise. Any deviation from the predicted path would be noticed as the object moves against the background stars, but by the time we detected it, the maneuver would already be complete. Whatever purpose it served would be accomplished. The hidden window meant that any such maneuver occurred without witnesses. This may be coincidence. It may be the inevitable result of orbital geometry and our planet's position, or it may be something else. The question is not whether the Obath effect is real. It is. We use it constantly in our own space program. The question is whether an interstellar visitor made use of it during the 2 weeks when no telescope on Earth could watch. Dark forest. In 1950, the physicist Enrico Fermi was having lunch at Los Alamos National Laboratory when the conversation turned to the question of extraterrestrial life. After some discussion of the probability of other civilizations existing in our galaxy, Fermi asked a question that has haunted scientists ever since. Where is everybody? This became known as the Fermi paradox. The galaxy is old, approximately 13 billion years. It contains hundreds of billions of stars, many of which have planets in habitable zones. Even if intelligent life is rare, even if it emerges on only a tiny fraction of suitable worlds, the sheer numbers suggest that civilization should be common, yet we see no evidence of anyone else. No signals, no artifacts, no visitors. Many explanations have been proposed. Perhaps life is rarer than we think. Perhaps intelligence is a cosmic accident, unlikely to repeat. Perhaps civilizations inevitably destroy themselves before becoming spacefaring. Perhaps the distances between stars are simply too vast to bridge. But there is another explanation, darker than the rest. In 2008, Chinese author Liu Cixin published a novel called The Dark Forest. It proposed a solution to the Fermi paradox that has since become one of the most discussed ideas in the literature of extraterrestrial intelligence. The universe, Liu suggested, is like a dark forest. Every civilization is a hunter stalking through the trees, moving silently, trying not to be noticed. Any civilization that reveals itself becomes a target. Any civilization that detects another faces a choice. The stakes are existential. The logic proceeds from simple premises. All life seeks survival. This is definitional. A species that did not prioritize its own continued existence would not last long enough to become a civilization. Resources are limited. Stars die. Planets can be destroyed. Even in a vast universe, the materials and energy needed for survival are finite. Competition is inevitable. Communication is slow. Interstellar distances are measured in light years. A message sent to another civilization might not receive a reply for decades or centuries. In that time, circumstances could change dramatically. The civilization you contacted as friends might become enemies. The technology you shared might be turned against you. Trust is impossible. You cannot verify the intentions of a civilization light years away. They cannot verify yours. Even if both parties genuinely desire peace, neither can be certain the other does. The uncertainty is fundamental and cannot be resolved. Given these premises, what is the rational course of action when you detect another civilization? The dark forest hypothesis answers brutally. You strike first. If you reveal yourself, you become a target. If you wait to assess the other civilization's intentions, they might develop weapons capable of destroying you before you can respond. If you attempt to communicate, you reveal your location and your technological level, providing valuable intelligence to a potential enemy. The only safe course is preemptive destruction. This logic creates a universe of terrified silence. Every civilization that survives does so by hiding. Every civilization that makes itself known is destroyed. The galaxy appears empty, not because we are alone, but because everyone who understands the rules is hiding from everyone else. It is a bleak vision. It may also be wrong. Critics have pointed out numerous problems with the dark forest hypothesis. It assumes a particular kind of risk aversion that may not be universal. It ignores the potential benefits of cooperation. It treats all civilizations as rational actors following the same logic, which seems unlikely given the diversity of life on Earth alone. But the dark forest hypothesis does not need to be correct for it to be relevant. It only needs to be possible. If even one civilization in the galaxy operates according to dark forest logic, the consequences would be severe. A single species with the technological capability and the willingness to destroy potential rivals could reshape the galactic landscape. Everyone else would either hide, be destroyed, or adopt the same strategy. And this brings us back to 3I/Atlas. If the dark forest hypothesis describes reality, what would a reconnaissance probe look like? It would not announce itself. It would not transmit signals. It would not display obvious signs of artificial origin. It would move through target systems quietly, gathering information, avoiding detection. It might disguise itself as a natural object. Comets are common in the universe. Every star system should have its own population of icy bodies, remnants from planetary formation scattered into the void by gravitational interactions. An interstellar comet would not be surprising. It would be expected. It would be the perfect camouflage for something else. A probe designed to look like. A comet would have a nucleus of rock and ice. It would outgas as it approached a star, developing a coma and tail. It would follow a trajectory consistent with gravitational physics. It would do comet things. But it might also do other things, hidden beneath the cometary appearance. It might carry instruments for observing planetary systems, cameras, spectrometers, radio receivers, sensors of types we cannot anticipate. The outgassing that makes it look like a comet could also obscure the heat signatures of active systems. It might carry payloads for deployment, small observers sent toward planets of interest, relays for transmitting collected data back to its origin, or something more direct. It might be designed to interact with the target star. This is where the sunspot becomes relevant again. In the dark forest, a civilization that wishes to neutralize a potential rival without revealing itself would prefer indirect methods. Direct attack reveals your existence and location. But if you could trigger natural-seeming catastrophe, the cause might never be traced to you. A solar event would be the perfect weapon. A sufficiently powerful coronal mass ejection could strip away a planet's atmosphere. It could sterilize the surface with radiation. Even a less extreme event, one comparable to the Carrington storm, could collapse the technological infrastructure of a civilization at Earth's level of development. Power grids destroyed, communications disrupted. The cascade effects could take years to recover from, and it would all look natural. The sun produces storms, sunspots appear and vanish. No external cause would be suspected. Is it possible to trigger such an event artificially? We do not know. Our understanding of solar physics is incomplete. We know that magnetic reconnection releases energy, but we cannot predict exactly when reconnection will occur or how powerful it will be. The sun is a chaotic system, sensitive to initial conditions, difficult to model. But our ignorance is not a guarantee of impossibility. A civilization millions or billions of years more advanced than ours might understand the sun better than we understand our own electrical circuits. They might have developed techniques for influencing stellar activity that we cannot imagine. Or they might simply wait. An object passing through a solar system could observe and report. The parent civilization could use that intelligence to predict when natural solar activity would provide an opportunity. No manipulation required, only patience and timing. I am speculating now. I want to be clear about that. There is no evidence that 3I/Atlas is a weapon. There is no evidence that it caused the sunspot AR-4294. There is no evidence that any civilization operates according to dark forest logic. What there is a framework for thinking about risk. The dark forest hypothesis suggests that the absence of evidence is not evidence of safety. It suggests that an advanced civilization might go to great lengths to avoid detection. It suggests that apparently natural phenomena might not be natural at all. These suggestions are disturbing. They are also unfalsifiable, which makes them poor science. You cannot prove that the universe is not a dark forest. The absence of hostile civilizations attacking us could mean they do not exist, or it could mean they have not found us yet, or it could mean they are acting through means we do not recognize. But the convergence of events in December 2025 invites consideration of scenarios we would normally dismiss. An interstellar object with 9 documented anomalies, a hidden window at perihelion when anything could have happened, a historic sunspot appearing as the object emerged from behind the sun, a trajectory bringing the visitor to its closest Earth approach just as the sunspot might return for another rotation. Each piece has a natural explanation, but the pattern, when viewed through the lens of the dark forest, looks like something else. It looks like careful positioning. It looks like plausible deniability. It looks like what a probe would do if it wanted to cause maximum damage while appearing to be a natural comet. I do not believe this is what is happening. The evidence does not support such a conclusion. The natural explanation is more likely than the dark forest scenario by a large margin. But I also cannot prove it is not happening. The geometry of the situation is suspicious. The timing is striking. The hidden window prevents us from knowing what occurred at perihelion. In the dark forest, the hunters move silently. They do not reveal themselves. They act through means that cannot be traced. If the dark forest is real, we would not know until it was too late. And so, we watch the sky. We track the interstellar visitor. We monitor the sunspot. We hope that our universe is not as dark as Liu Cixin imagined. But hoping is not knowing. And the silence between stars offers no reassurance. There is a thought experiment that illustrates the dark forest logic with uncomfortable clarity. Imagine you are alone in a vast wilderness at night. You know there are other people somewhere in the darkness. You cannot see them. You cannot hear them. You do not know how many there are or what their intentions might be. Now imagine you have a flashlight. Do you turn it on? If you turn it on, you can see your immediate surroundings. But you also reveal your position to everyone else in the wilderness. Anyone watching will know exactly where you are, and you have no idea who might be watching or what they might do with that information. The dark forest hypothesis suggests that the rational choice is to stay dark. The risk of revelation outweighs the benefit of illumination. Even if most of the others in the wilderness are friendly, you cannot be certain. And if even one is hostile, revealing yourself could be fatal. This is the logic that governs interstellar relations in Liu's novels. It is the logic that explains the cosmic silence in his universe. Everyone who survives does so by staying hidden. Everyone who makes themselves known is destroyed. Is this logic applicable to the real universe? The critics say no. They point out that the assumption of universal hostility is implausible. They note that cooperation often provides greater benefits than competition. They argue that a civilization advanced enough for interstellar travel would likely have transcended the zero, some thinking of primitive species. These objections have merit. The dark forest hypothesis assumes the worst about the nature of intelligence. It ignores the possibility of interstellar law, of galactic civilization, of norms against aggression. It posits a universe ruled by fear rather than reason. But the hypothesis does not need to describe all civilizations. It only needs to describe some. A single aggressive species willing to destroy potential rivals would be enough to create the observed silence. Everyone else would hide, whether from shared paranoia or from prudent self-preservation. And if such a species existed, what would their reconnaissance look like? It would look natural. It would not announce itself. It would gather information without revealing its presence. It would use the target system's own phenomena to achieve its goals. A comet that is not quite a comet. A solar event that is not quite random. A convergence that is not quite coincidental. I'm not claiming that 3i/Atlas is such a probe. The evidence does not support that claim. I'm only noting that if such a probe existed, we might not be able to distinguish it from a natural object until it was too late. The dark forest is a thought experiment, not a proven fact. But thought experiments have value. They force us to consider possibilities we might otherwise dismiss. They expand the space of what we consider possible, and in that expanded space the convergence of December 2025 takes on different shades of meaning. The quiet before. There is a phenomenon familiar to anyone who has weathered a major storm. The hours before the worst arrives often feel unnaturally calm. The wind drops, the pressure stabilizes, animals grow quiet, the world seems to hold its breath, waiting for something to break. We may be in such a moment now. As of early December 2025, the sunspot complex AR4294 through 4298 remains active but has not produced a Carrington class event. Multiple M class flares have erupted. Several C class events have been recorded. On December 1st, the adjacent region AR4299 announced its return with an X1.9 flare, a significant release of energy that caused radio blackouts over portions of the daytime Earth. But the major event, the one that could reshape our technological infrastructure, has not occurred. The beta, gamma, delta magnetic configuration stores enormous energy. The potential remains. The release has not come. This is not unusual. Sunspots often build a high complexity without producing major flares. The energy can dissipate gradually through smaller events. The magnetic configuration can simplify as field lines reconnect in minor cascades. Not every loaded gun fires, but the gun remains loaded. Meanwhile, 3I/Atlas continues its journey outward from the Sun. Having emerged from the hidden window of solar conjunction in early November, the object is now visible to Earth-based observers during evening twilight. The coma, the fuzzy envelope of gas and dust surrounding the nucleus, has grown brighter as expected following the intense heating of perihelion. The trajectory remains consistent with gravitational physics. No propulsive maneuvers have been detected. No secondary objects have been confirmed. The main body appears intact, a nucleus estimated between 400 meters and 6 kilometers in diameter, depending on assumptions about reflectivity and density. December 19th approaches. On that date, 3I/Atlas will reach its closest point to Earth at a distance of approximately 269 million kilometers. In everyday terms, that is about 1.8 times the distance from Earth to the Sun. It is not close in human terms. You will not be able to see it with the naked eye. It will not fill the sky like a second moon. But in terms of interstellar objects, this is an intimate encounter. We have never had such a close approach by a confirmed visitor from beyond our solar system. Oumuamua was detected only after it had already passed its closest point and was speeding away. Borisov never came particularly close to Earth. 3I/Atlas offers an unprecedented opportunity for study. The observation campaign is in full swing. The Hubble Space Telescope has been allocated time for imaging. The James Webb Space Telescope is gathering infrared data that could reveal details about the nucleus composition. Ground-based observatories around the world are tracking the object's position with exquisite precision, refining the trajectory to look for any deviation from gravitational predictions. The European Space Agency's JUICE mission, currently en route to Jupiter, passed within 64 million kilometers of 3I/Atlas in early November. Its cameras captured images that are still being analyzed. The data is expected to be released in early 2026. NASA's Juno spacecraft, currently orbiting Jupiter, will have an opportunity to observe the object when it makes its closest approach to that planet in March 2026. By then, 3I/Atlas will be well on its way out of the solar system, but any remaining activity should still be detectable. We are gathering data, we are watching carefully, we are learning what we can while the opportunity exists, and yet the two events continue to converge. The sunspot complex AR4294 is slowly rotating toward the western limb of the Sun. In approximately 2 weeks from today, it will pass out of view, carried by the Sun's rotation to the far side where its tantrums cannot directly affect Earth. This provides a window of relative safety. Any flares that occur while the sunspot faces away from us will send their energy into empty space, not toward our planet. But sunspots can survive multiple rotations. The magnetic structures that create sunspots persist beneath the solar surface even when the visible manifestation disappears. If AR4294 remains coherent during its passage across the far side, it could return to the Earth, facing disk around late December. The timing would coincide with the days following the closest approach of 3I/Atlas. The probability of this return is uncertain. Sunspots decay, magnetic configurations simplify. Some large regions dissipate entirely during a single solar rotation. Others persist for months, circling the sun repeatedly, producing flares each time they face Earth. The forecasters at NOAA's Space Weather Prediction Center are monitoring the situation. Their assessments are updated daily, incorporating the latest observations of magnetic field strength and complexity. As of this recording, the outlook remains elevated but not extreme. G1 to G2 geomagnetic storm conditions are possible from ongoing activity. The chance of a major event remains low. Low is not zero. Think about that for a moment. We have a sunspot complex 90% the size of the one that caused the Carrington event. It has the most dangerous magnetic classification our systems can assign. It is currently facing Earth and will return to face us again in approximately 4 weeks. And an interstellar object with 9 documented anomalies will reach its closest approach to our planet in the intervening period. The timing creates a window. From December 19th, when 3I/Atlas reaches closest approach, through approximately December 25th, when AR 4294 could rotate back into view, Earth finds itself at the intersection of 2 unusual events. One is certainly natural, the other is almost certainly natural. Together they create a convergence that feels significant even if we cannot prove it is meaningful. I want to be careful here. Nothing has happened yet. The sunspot has not produced a Carrington-class flare. The interstellar object has not deviated from its expected trajectory. All observations are consistent with natural phenomena following natural laws. But we are in the quiet before. History is full of moments that seemed calm until they were not. The hours before major earthquakes often feel ordinary. The days before financial crises often seem stable. The months before pandemics often proceed as normal. We are poor at recognizing the build-up to events that have not yet occurred. The infrastructure that protects us from space weather is better than it was in 1859, but it remains inadequate. Satellites can be placed in safe mode during solar storms, reducing their vulnerability. Power grid operators can take protective measures if given warning. But the warning time for a fast-moving coronal mass ejection can be as little as 15 minutes. That is not enough time to implement comprehensive protections. If a Carrington-class event occurred tomorrow, we would face consequences ranging from severe to catastrophic. The studies have been done. The estimates have been published. $2.6 trillion in economic damage. Power outages lasting months. Cascading failures in communications, transportation, finance, and healthcare. The recovery would take years. This is not fear-mongering. This is the assessment of experts who have studied the problem. The threat is real, whether or not it materializes this month or this year or this decade. And now we wait. 3I/Atlas is approaching. The sunspot complex continues to rotate. The space weather forecasters continue to monitor. The observation campaigns continue to gather data. The world continues to function, dependent on electromagnetic systems that could fail without warning. The quiet before is not peace. It is suspense. Something may happen in the coming weeks, a flare of historic proportions, an anomaly in the trajectory of the interstellar visitor, a discovery that changes our understanding of what we are facing, or nothing may happen. The sunspot may decay. The object may continue on its predicted path. December may pass without incident, and the convergence will be nothing more than coincidence, a statistical fluke that meant nothing. We cannot know which outcome awaits us. We can only watch and prepare and hope that the quiet continues. But somewhere in the back of our minds, we know that the quiet never lasts forever. Storms come, events occur. The calm before is always followed by something else. December 19th approaches. The ancient traveller draws near. The wound on the sun still bleeds energy into space, and we wait, in the quiet, for whatever comes next. What the probes will see. The eyes we have turned toward 3I/Atlas represent the most sophisticated observation campaign ever assembled for an interstellar object. Dozens of instruments, spanning multiple space agencies and ground-based observatories, are gathering data that will take years to fully analyze. For a brief window in late 2025, the third visitor from beyond our solar system commands attention from the best equipment humanity has ever built. Let me walk through what we are deploying and what we hope to learn. The Hubble Space Telescope, launched in 1990 and still operating after more than 3 decades, offers resolution that ground-based telescopes struggle to match. Atmospheric turbulence blurs the view from Earth's surface. Hubble, orbiting above the atmosphere, sees with crystalline clarity. For 3I/Atlas, Hubble can potentially resolve details of the coma structure, the distribution of dust around the nucleus, the geometry of any jets venting from the surface, changes in brightness over time that might indicate rotation of an irregularly shaped body. The telescope has already captured images during the object's inbound journey, and additional observations are scheduled for the December closest approach. The James Webb Space Telescope, launched in 2021, extends our vision into the infrared. Heat radiates at wavelengths our eyes cannot see, but Webb can detect with exquisite sensitivity. For a cometary object, infrared observations reveal the chemical composition of outgassing material. Water, carbon dioxide, carbon monoxide, and other volatiles each leave distinct spectral signatures. Webb has already confirmed that the coma of 3I/Atlas is dominated by carbon dioxide rather than water. This is unusual for a comet from our solar system, where water ice typically drives activity. But for an object that has spent billions of years in the cold of interstellar space, the volatile inventory may be different. Carbon dioxide sublimates at lower temperatures than water, suggesting it might be the first material to become active as the object approached the Sun. The infrared observations can also constrain the size and thermal properties of the nucleus. How much heat is the surface absorbing versus radiating? What is the albedo, the reflectivity of the surface? These parameters help distinguish between different compositional models. Ground-based telescopes contribute their own capabilities. The Very Large Telescope Array in Chile, the Keck Observatory in Hawaii, the Gemini telescopes in both hemispheres all have turned toward 3I/Atlas at various points in its journey. Spectroscopy from these facilities can detect specific molecular species in the coma with high precision. Of particular interest is the nickel-to-iron ratio that has been measured in the outgassing material. As mentioned earlier, this ratio is unusually high for 3I/Atlas compared to typical comets. Further observations may clarify whether this reflects the bulk composition of the nucleus or some surface phenomenon related to the interstellar environment. Beyond the traditional observatories, a constellation of specialized missions are contributing data. The Parker Solar Probe, which passes closer to the Sun than any previous spacecraft, observed 3I/Atlas during the perihelion passage from its unique vantage point. The probe is designed to study the solar corona and solar wind, but its instruments can also detect objects passing through its field of view. Any observations from Parker during the hidden window would be particularly valuable. The SOHO satellite, the Solar and Heliospheric Observatory, has been monitoring the Sun from the first Lagrange point since 1995. Its coronagraphs, instruments that block the direct light of the solar disk to reveal the faint corona, captured images of 3I/Atlas as it passed behind the Sun. These images show the object brightening as it approached perihelion, consistent with increased cometary activity from solar heating. The Punch mission, launched in 2024, is designed to study the connection between the solar corona and the heliosphere. Its instruments detected 3I/Atlas in late October as the object neared perihelion. The data is still being analysed. The European Space Agency's JUICE mission offers a unique opportunity. Originally launched to study Jupiter's icy moons, JUICE is currently in the cruise phase of its journey. By fortuitous timing, its trajectory brought it within 64 million kilometres of 3I/Atlas on November 4th, just days after perihelion. JUICE carries a suite of instruments that were not designed for cometary observation, but can be adapted for the purpose. The Janus Visible Imager can capture high-resolution images. The MAGIS infrared spectrometer can analyse thermal emission. The SWI submillimeter wave instrument can detect certain molecules in the coma. The JUICE observations represent the first post, perihelion data from a close encounter with the object. The analysis is ongoing, and results are expected in early 2026. These images may reveal details invisible to Earth-based telescopes, including any changes in the nucleus resulting from perihelion heating. Looking further ahead, NASA's Juno spacecraft at Jupiter will have an observation opportunity in March 2026. By then, 3I/Atlas will be receding from the Sun, its activity diminishing as it cools. but any remaining outgassing should still be detectable, and the trajectory data from Juno will further refine our understanding of the object's path. What are we looking for? At the most basic level, we want to characterize the object. Size, shape, composition, rotation, activity patterns. These parameters tell us about the environment where 3I/Atlas formed and the history of its journey through interstellar space. But we're also looking for anomalies. Any deviation from the expected trajectory would be significant. Comets often show none, gravitational acceleration due to outgassing. The jets of material from the surface push the nucleus like tiny rocket engines. This effect can be measured and modelled. If 3I/Atlas shows acceleration that cannot be explained by observed outgassing, that would require explanation. Oumuamua, the first interstellar object, displayed exactly such anomalous acceleration. The deviation was small but measurable. Several explanations were proposed, including outgassing of invisible volatiles, but none was fully satisfactory. The mystery of Oumuamua's acceleration remains unresolved. Will 3I/Atlas show similar anomalies? The preliminary data suggests the trajectory is consistent with gravitational physics, but the analysis is ongoing. Any deviation would immediately become the focus of intense investigation. We're also looking for secondary objects. If 3I/Atlas released material during the perihelion passage, whether through natural fragmentation or hypothetical deployment, that material should become visible as it separates from the main nucleus. Tidal forces and radiation pressure would cause fragments to drift apart over time. By December, any significant separations should be detectable. So far, no confirmed fragments have been observed. The main body appears intact, but the surveys continue, and any new detections would be immediately reported. We are looking for spectral signatures that might indicate unusual chemistry. The nickel anomaly is already documented. Are there other unexpected features in the spectrum? Any absorption or emission lines that do not fit standard cometry models would attract attention. Even the absence of expected features could be informative, and we are looking for anything that does not fit. This is the essence of exploratory science. We have models that predict what a natural interstellar comet should look like. We compare observations to those models. Where they match, we learn about cometry physics. Where they differ, we learn something new. The data flowing back from all these instruments will take months to fully analyse. The December observations will provide the closest views we will ever have of 3I/Atlas. After the closest approach, the object will begin to recede, growing fainter week by week until it is beyond the reach of even our most powerful telescopes. We have one chance to study this visitor in detail. The international astronomy community understands this. Resources have been allocated, observation time has been scheduled, the data collection is underway. What the probes will see depends on what is there to be seen. If 3I/Atlas is a natural comet, the observations will reveal the properties of an ancient icy body from another star system. We will learn about planet formation in distant environments. We will add to our understanding of the galaxy's chemical inventory. If 3I/Atlas is something else, the observations might reveal anomalies that demand explanation, unexpected features, unexplained behaviour, data that does not fit any natural model. We do not know which outcome awaits us. We can only point our instruments and gather the data. The probes are watching, the telescopes are recording, and in the data streams flowing from satellites and observatories around the world, the answer may already be written, waiting for us to read it. The analysis pipeline for cometry observations is well established, but 3I/Atlas presents unique challenges. The object is moving fast. At over 100,000 miles per hour relative to the Sun, it crosses significant portions of the sky from night to night. Tracking requires continuous updating of telescope pointing. The exposure times must be short enough to avoid motion blur while still gathering enough light for meaningful analysis. The coma obscures the nucleus. Unlike asteroids, which present bare surfaces to our instruments, comets surround themselves with halos of gas and dust that scatter and absorb light. Determining the properties of the nucleus requires modelling and subtracting the coma contribution, a process that introduces uncertainties. The distance is large. Even at closest approach, 3I/Atlas will be nearly 270 million kilometres from Earth. At that distance, angular resolution is limited. Features that would be obvious on a nearby object become indistinguishable points of light. But the instruments are sophisticated, and the techniques have been refined over decades of cometry observation. Spectroscopy provides the most detailed chemical information. By spreading the light from the coma into its component wavelengths, astronomers can identify the molecules present. Each species absorbs and emits light at characteristic frequencies, creating a fingerprint that can be read by sensitive instruments. For 3I/Atlas, the spectroscopic data has already revealed the unusual nickel-to-iron ratio mentioned earlier. Further observations may clarify whether this reflects the bulk composition of the nucleus or a surface phenomenon. The answer has implications for understanding where the object formed and what conditions prevailed there. Photometry tracks brightness changes over time. If the nucleus is irregularly shaped, as most cometary nuclei are, its brightness will vary as different faces rotate toward the observer. The period of variation reveals the rotation rate. The amplitude of variation constrains the shape. For 3I/Atlas, photometric observations have detected periodic brightness fluctuations that some have called a heartbeat. The period appears to be on the order of hours, consistent with a slowly rotating nucleus. Whether this represents natural rotation or something else remains to be determined. Astrometry measures position with extreme precision. By tracking the object against background stars, astronomers can refine the orbital parameters and detect any deviation from gravitational predictions. This is the technique that revealed the anomalous acceleration of Oumuamua. For 3I/Atlas, astrometric monitoring is ongoing. The trajectory appears consistent with gravitational physics so far, but the critical observations will come in the weeks after closest approach, when any accumulated deviation would be most apparent. Polarimetry measures the orientation of light waves. When light scatters off particles, it becomes partially polarized. The degree and type of polarization provides information about particle size and composition. The extreme negative polarization of 3I/Atlas is one of its documented anomalies, suggesting dust properties unlike any previously observed comet. Each technique provides a piece of the puzzle. Together, they paint a portrait of the visitor that will be analysed for years after it departs. The timeline is unforgiving. 3I/Atlas will be at its brightest and closest for only a few weeks. After that, it will recede, fading against the background stars until it falls below our detection threshold forever. We have one chance to understand this object. The observation campaign represents the best effort our species can muster. Whatever answers exist will be found in the data now being collected, or they will be lost to the interstellar void along with the object itself. The Fibonacci Whisper. In the weeks following the discovery of 3I/Atlas, something remarkable happened on the internet. The usual flow of misinformation accelerated into a torrent. Claims multiplied, theories proliferated. And somewhere in the noise, a particular story began to circulate with viral intensity. The story claimed that 3I/Atlas was emitting signals, not just any signals. The claims specified regular pulses at intervals of 147 seconds. The pulses supposedly contained numerical sequences, specifically the Fibonacci numbers, a series where each number is the sum of the two preceding it. The frequency was said to be 1420 MHz, the hydrogen line, known in scientific circles as the most likely frequency for interstellar communication, because it corresponds to the emission spectrum of neutral hydrogen. The story spread across social media platforms. It was picked up by tabloid websites. It was attributed to unnamed scientists, to leaked documents, to supposed intercepted communications. In some versions, the signals had been decoded to reveal messages. Observe, prepare, understand, the gate awaits. None of this is confirmed. I want to be absolutely clear about the status of these claims. There are no peer-reviewed papers documenting signal detection from 3I/Atlas. There are no official announcements from observatories or space agencies confirming electromagnetic emissions of artificial origin. The stories circulating online do not cite sources that can be verified. This does not mean the stories have no basis. It means the basis cannot be confirmed. The physicist Michio Kaku was cited in some versions of the story, allegedly describing pulses that should not exist. But Kaku has not published any scientific paper on the subject, and the quotes attributed to him appear to originate from viral video content rather than academic sources. Avi Loeb has discussed what he calls the heartbeat of 3I/Atlas, referring to observed brightness variations that pulse at regular intervals. This is a real observation. Cometary nuclei often display periodic brightness changes as they rotate, with different faces presenting different reflectivity to observers. The period of variation can be measured, providing information about the rotation rate of the nucleus. But a rotating comet is not the same as an artificial signal. The psychology of why these claims spread is worth examining. We are a species that evolved to find patterns, even when none exist, faces in clouds, meaning in noise. We are also a species that has spent decades imagining contact with extraterrestrial intelligence, through science fiction, through SETI programs, through speculation about our place in the cosmos. When an unusual object arrives from interstellar space, the template is already in place. We have been primed to expect visitors. And when the visitor displays anomalies, when its trajectory seems suspicious and its composition seems strange, the leap to artificial origin is almost irresistible for some minds. Approximately 40% of social media discussion about 3i/Atlas invokes extraterrestrial intelligence in some form. This is not a fringe position, it is a substantial fraction of the public conversation. The desire for contact runs deep, but desire is not evidence. What would a genuine artificial signal look like? This question has occupied SETI researchers for decades. The challenge is distinguishing intentional communication from natural phenomena and from terrestrial interference. Natural sources can produce remarkably regular patterns. Pulsars, rapidly rotating neutron stars, emit pulses of radio energy at intervals as precise as atomic clocks. When pulsars were first detected in 1967, the regularity of their signals led to brief speculation about artificial origin. They were nicknamed LGM, for little green men, before the natural explanation was established. Artificial sources would presumably carry information. Random pulses are not communication. To qualify as a signal, there should be structure that encodes meaning. Mathematical sequences are often proposed as a universal language, since mathematics should be the same everywhere in the universe. The Fibonacci sequence, the prime numbers, geometric ratios, these might serve as a calling card to prove artificial origin. But detecting information requires ruling out all natural and instrumental explanations first. This is difficult. Instruments have noise. Electronics produce spurious signals. Software has bugs. The history of SETI includes numerous false alarms where exciting detections turned out to have mundane explanations. The WOW signal of 1977 remains the most famous unexplained detection. A radio telescope in Ohio recorded a burst of intensity at the hydrogen line that lasted 72 seconds and has never been repeated. Despite decades of follow-up observations, the source has never been identified. It might have been a spacecraft, transmission reflected from debris. It might have been a natural phenomenon not yet understood. It might have been equipment malfunction, or it might have been something else entirely. The WOW signal demonstrates how difficult it is to confirm artificial origin. A single observation, no matter how striking, is not enough. Repeatability is essential. Independent verification is required. All alternative explanations must be ruled out. For 3i/Atlas, the bar is even higher. The object is moving. The geometry is changing. Any signal that might be detected one day might not be detectable the next as the orientation changes, and the object will be observable for only a few more months before it recedes beyond our instrument's reach. The claims circulating online do not meet scientific standards. They are not supported by documented observations. They have not been verified by independent observers. They consist largely of screenshots, viral videos, and anonymous sources. But the claims reflect something real about human nature. We want there to be signals. We want the interstellar visitor to be meaningful. We want the universe to contain intelligence beyond our own. This desire is not irrational. The probability arguments that underlie the Fermi paradox suggest that intelligence should be common. The sheer number of stars, the abundance of planets, the long history of the galaxy, all point toward a universe that should be teeming with life. Our failure to detect that life creates cognitive dissonance. Surely they must be out there. Surely we should have heard something by now. And so, when an interstellar object arrives, displaying anomalies that mainstream science cannot fully explain, the temptation to read it as contact becomes overwhelming for some observers. The viral claims are not evidence of signals. They are evidence of hope. Let me offer a framework for evaluating future claims. First, consider the source. Published peer-reviewed research is more reliable than anonymous social media posts. Named scientists speaking on the record are more reliable than quotes from viral videos. Official announcements from observatories and space agencies are more reliable than tabloid speculation. Second, consider the verification. Has the claimed observation been confirmed by independent observers using different equipment? A single detection could be instrumental error. Multiple independent detections are much harder to explain away. Third, consider alternative explanations. Have natural phenomena been ruled out? Have equipment malfunctions been investigated? Have terrestrial sources of interference been eliminated? The bar for claiming artificial origin is high, precisely because the implications are enormous. Fourth, consider the information content. Random noise is not a signal. Regular pulses could have natural explanations. Genuine communication would presumably carry structured information that could be decoded, not just rhythmic patterns. By these standards, the current claims about signals from 3I/Atlas do not hold up. The observations that have been documented are consistent with natural cometary behavior. The viral claims have not been verified. The extraordinary evidence required for extraordinary claims has not been presented. This does not mean the claims are necessarily false. It means they have not been established as true. The distinction matters. 3I/Atlas will continue to be observed in the coming weeks. If genuine signals are detected, they will be documented, verified, and announced through proper scientific channels. The world will know. Until then, the Fibonacci whisper remains just that. A whisper in the noise, a hope dressed as rumour, a desire for contact that runs ahead of the evidence. The silence of the cosmos continues, and in that silence, we project our dreams of what we wish to hear. The history of SETI is a history of false hopes and dashed expectations. For over 60 years, radio telescopes have scanned the sky for signals of artificial origin. Billions of frequencies have been sampled. Billions of star systems have been surveyed. The result has been silence, broken only by occasional anomalies that could not be confirmed. The WOW signal remains the gold standard of unexplained detections. On August 15th, 1977, astronomer Jerry Eman was reviewing printouts from the Big Ear radio telescope at Ohio State University when he noticed something extraordinary. A strong signal at 1420 MHz, the hydrogen line, had appeared briefly and then vanished. The intensity was far above background noise. The bandwidth was narrow, suggesting artificial origin. Eman circled the reading and wrote "WOW" in the margin. The follow-up observations found nothing. The signal has never been detected again despite decades of attempts. Explanations have been proposed, including a secret military satellite, a natural radio source, and interstellar hydrogen excited by a passing comet. None is fully satisfactory. More recently, the Breakthrough Listen project has conducted the most comprehensive SETI survey in history. Funded by technology entrepreneur Yuri Milner, the project has access to some of the world's largest radio telescopes. Millions of stars have been observed. The data analysis is ongoing. So far, no confirmed signals have been announced. The silence continues. But the absence of evidence is not evidence of absence. Our surveys cover only a tiny fraction of the electromagnetic spectrum. Our search strategies assume that alien civilizations would communicate in ways we can recognize. Our instruments have limited sensitivity. A civilization that wished to remain hidden could easily do so. This is why the claims about 3I/Atlas attract such attention. An interstellar object provides a different kind of contact opportunity. Not a signal travelling at the speed of light, but a physical artifact travelling at a mere fraction of that speed, something we can observe directly if we know what to look for. The claims circulating online represent a form of wishful thinking, a desire to find meaning in ambiguous data. But the underlying impulse is understandable. We have been waiting a long time for contact. The silence has grown heavy. When something unusual arrives from interstellar space, the hope that it might be meaningful is almost irresistible. Science requires that we resist that hope, at least until the evidence supports it. The burden of proof for extraordinary claims is high. The standards of evidence are rigorous. Feelings and desires do not constitute data. And yet the questions persist. 9 anomalies, a hidden window, a sunspot of historic proportions, a December convergence. The data does not support claims of artificial signals, but the data also does not rule out artificial origin. We are in a state of uncertainty, where the natural explanation is more likely but not certain. This uncertainty may never be resolved. 3I/Atlas will leave our solar system. It will not return. Whatever secrets it carries will depart with it, beyond the reach of our instruments, beyond the grasp of our understanding. We will be left with questions and probabilities, not answers and certainties. That is often the nature of science. The universe is not obligated to provide closure. The Convergence. We stand now at the intersection of two trajectories. One has been travelling for 8,000 years, crossing the void between stars at speeds no human technology has ever achieved. The other emerged from the churning magnetic depths of our own sun, a wound on a familiar face that has appeared precisely as the visitor draws near. 3I/Atlas will reach its closest approach to Earth on December 19th. AR 4294 may return to the Earth facing disk around Christmas. The Convergence is not a collision. It is a coincidence of timing that invites questions we cannot answer but cannot ignore. Let me state clearly what we know. We know that 3I/Atlas is an interstellar object, the third ever detected, moving through our solar system on a hyperbolic trajectory that will carry it back into the void from which it came. We know its path brought it within 5 degrees of the ecliptic plane, close to several planets, and to its closest approach to the Sun during a 2-week window when observation from Earth was impossible. We know the object displays 9 documented anomalies: unusual trajectory, unusual timing, unusual composition, unusual mass, unusual polarization, unusual survival, unusual color, unusual activity patterns, unusual in ways that cluster together around this single visitor. We know that the sunspot complex AR4294 through 4298 is one of the largest and most magnetically complex active regions of solar cycle 25. We know it appeared as the interstellar object emerged from behind the Sun. We know it is capable of producing X, class flares, and potentially Carrington, class events. We know that a Carrington, class event in the modern world would be catastrophic. Power grids destroyed, satellites disabled, communications disrupted, an infrastructure dependent on electromagnetism brought to its knees by a magnetic storm. These things we know. What we do not know is whether they are connected. The scientific consensus holds that they are not. The Sun produces large sunspots during solar maximum. Interstellar objects follow gravitational trajectories without regard to solar activity. The timing is coincidence. The Convergence is meaningless. This may be correct. It is probably correct. The natural explanation should be the default until and unless the evidence demands otherwise. But the evidence is ambiguous. The hidden window at perihelion means we cannot know what happened during the most dynamic phase of the object's journey. The Obath effect means that perihelion was the optimal moment for any propulsive action. The dark forest hypothesis means that a sufficiently advanced civilization might use natural-seeming phenomena to achieve its goals. We are speculating now. We have been speculating throughout this journey. Speculation is not science, but it is also not nothing. It is the exploration of possibility space, the mapping of what might be true before we have the data to determine what is true. And the possibilities are striking. If 3I/Atlas is a natural comet, then December 2025 is a remarkable coincidence, an interstellar visitor and a historic sunspot converging on Earth by pure chance. The universe occasionally produces such alignments. They mean nothing, they signify nothing. They are the random clustering of events in a cosmos indifferent to human pattern, seeking. If 3I/Atlas is something else, the Convergence takes on different meaning. A reconnaissance probe timing its closest approach to coincide with potential solar disruption. A weapon using our own sun against us. A test of our observational capabilities and our response to unusual events. I do not believe the second interpretation is correct. The evidence does not support it. But I also cannot prove it is wrong. The geometry prevents proof. The timing invites suspicion. The accumulated anomalies resist easy dismissal. What should we take from this? Perhaps humility. We have been spacefaring for less than 70 years. We have been aware of interstellar objects for less than 10. Our understanding of solar physics, of cometary behavior, of the possibilities for life in the universe, all of it is preliminary. We see through a glass darkly, as the ancient text says. We know in part. Perhaps vigilance. The sunspot remains active. The threat of space weather is real regardless of any interstellar visitor. Our infrastructure is vulnerable. Our preparations are inadequate. Whether or not December 2025 produces a major event, future Decembers will. The Carrington equation does not care about our readiness. Perhaps wonder. We live in a universe where objects from other star systems occasionally pass through our cosmic neighborhood. They carry information about environments we can never visit, chemistries we can only sample, histories that stretch back to before our sun existed. 3I/Atlas formed 7 to 11 billion years ago in a stellar system that may itself have died long before Earth was born. We are witnessing a fragment of cosmic history, a messenger from the deep past, perhaps gratitude. We have instruments capable of detecting these visitors. We have observatories that can track them across the solar system. We have space agencies willing to allocate resources for their study. A century ago, 3I/Atlas would have passed unnoticed. A millennium ago, its arrival would have been entirely invisible. We are the first generation of humans with the capacity to see what is coming. The convergence of December 2025 may be remembered as the moment when an interstellar visitor and a solar wound coincidentally aligned. A curiosity for future historians. A footnote in the long story of solar-terrestrial relations, or it may be remembered as something else. We do not know which story we are living. We cannot read the chapter headings from inside the narrative. We can only observe and record and try to understand. 3I/Atlas will pass closest to Earth in less than 2 weeks. The sunspot will rotate out of view and may return for another pass. The data will continue to flow from observatories around the world. The analysis will continue for months and years. Whatever happens next, we will be watching. And now, as we draw toward the close of this journey, let me offer some final thoughts. The universe is vast. The silence between stars is deep. We send our signals outward and receive nothing in return. We build our detectors and strain for any hint of intelligence beyond our own. And still the cosmos offers no reply. But occasionally something comes to us. Not a signal, not a message. Something physical, something real. An object from the void passing through our small corner of the galaxy, visible for a few months before vanishing back into the dark. These visitors do not answer our questions. They multiply them. They remind us how much we do not know, how vast our ignorance, how preliminary our understanding. 3I/Atlas will leave our solar system. It will continue its journey into interstellar space. In a few thousand years, it will pass near another star. In a few million years, it will have crossed a significant portion of the galaxy. It carries with it whatever secrets it possesses, whether those secrets are the natural properties of an ancient comet or something stranger. We will not follow it. We do not have the technology. We can only watch it recede, growing fainter, until it falls below our detection threshold and is gone. But we will remember. We will remember the July discovery. We will remember the autumn approach. We will remember the hidden window at perihelion. We will remember the sunspot that appeared. We will remember the December convergence. And we will wonder, perhaps forever, whether we understood what we were seeing. Thank you for joining me on this exploration. The questions we have raised tonight do not have easy answers. Perhaps they do not have answers at all. But the asking itself has value. The wonder itself is worthwhile. If you have found this content meaningful, please consider liking and subscribing. Your engagement helps these conversations reach others who share our curiosity about the cosmos. The universe is strange. The universe is beautiful. The universe keeps secrets we may never unlock. And tonight, as December unfolds and two trajectories continue their convergence on our small world, we add one more mystery to the collection. Sleep well, dream of stars, and remember that the darkness between them is not empty. Something is always passing through. In the grand scheme of cosmic time, our moment of observation is infinitesimal. The universe has existed for nearly 14 billion years. Our species has been watching the sky with scientific instruments for less than 5 centuries. The window during which we could detect interstellar visitors is vanishingly small. And yet, in this tiny window, we have now seen 3. Oumuamua arrived in 2017, a tumbling object of unusual shape that accelerated away from the sun in ways we could not fully explain. It came and went before we understood what we were seeing, a blur at the edge of perception, raising questions that remain unanswered. Borisov followed in 2019, a more traditional comet with a tail and coma, offering less mystery, but confirming that interstellar visitors were not unique. Now 3I/Atlas passes through our cosmic neighbourhood, larger than its predecessors, stranger in its properties, arriving during solar maximum with a trajectory that brings it closer to Earth than any interstellar object before. The frequency is notable. 3 objects in 8 years, when our detection capabilities were non-existent before 2017. Either we have become remarkably good at finding these visitors, or they are more common than we ever imagined, or something else is happening. The natural explanation suggests that interstellar objects are abundant, numbering perhaps trillions within our solar system at any given moment, most too small and dark to detect. We see only the largest and most active, the tip of an enormous iceberg. This explanation may be correct. It is consistent with our understanding of planetary formation and the ejection of debris into interstellar space. Every star system generates such debris. The galaxy should be awash in small bodies wandering between the stars. But the natural explanation does not account for all the anomalies. It does not explain why Oumuamua accelerated. It does not explain why 3I/Atlas has such unusual chemistry. It does not explain the timing of the sunspot. Perhaps there is nothing to explain. Perhaps we are finding patterns in noise, seeing connections where none exist. The human mind evolved to detect threats, and it often detects threats that are not there. Or perhaps something is happening that we do not yet understand. The universe is vast and old. The possibilities for life are enormous. The silence of the cosmos may mean we are alone, or it may mean we are not listening correctly, or it may mean something is listening to us. We do not know. We may never know. But we continue to watch, because watching is what we do. It is why Richard Carrington built his observatory. It is why the Atlas telescope scans the sky night after night. It is why generations of scientists have devoted their lives to understanding the cosmos. The convergence of December 2025 may be nothing more than coincidence, or it may be the most important event in human history. We cannot tell the difference from inside the moment. We can only gather data, test hypotheses, and remain open to possibilities we have not yet imagined. The interstellar visitor continues its journey. The sunspot continues to rotate. The Earth continues to spin beneath both, fragile and beautiful, home to the only intelligence we know for certain exists in the universe. Whatever comes next, we will face it together. And perhaps that is the most important lesson of all. The universe is vast and indifferent. Stars explode, planets collide, civilizations may rise and fall across billions of years without ever meeting. We are small and fragile, clinging to a thin layer of rock and water around an ordinary star in an unremarkable corner of a galaxy that itself is just one among hundreds of billions. But we are here. We are watching. We are asking questions. The interstellar visitor does not care about our curiosity. The sun does not care about our vulnerability. The physics of orbital mechanics and magnetic reconnection unfolds without regard for human hopes or fears. And still we watch. Still we wonder. Still we reach toward understanding, even knowing that understanding may forever elude us. This is who we are. This is what we do. This is why the questions matter, even when the answers remain beyond our grasp. The convergence continues. The data accumulates. The mystery deepens or resolves. Time will tell which story we are living. Time will reveal whether December 2025 was coincidence or consequence. Until then, we watch the sky. We track the visitor, we monitor the sun, and we remember that the darkness between stars is not empty. It never was. The contents of this video are for informational and entertainment purposes only. The speculative scenarios discussed represent possibilities, not predictions. Always consult official sources for space weather alerts and scientific findings. Good night.